Hello, here are notes for Geometry 3.4 section. We're still in our transformation unit, although we're going to go back a little bit and talk about some symmetry. We were talking about rotations last time, so we're going to talk about some rotational symmetry. And it's with rotational symmetry, the shape or image can be rotated and it still looks exactly the same. In other words, it lands on top of itself and you wouldn't even see the difference. That's what it means. But let's go over to our comic, okay, and to our extra credit for the day. But here's the comic, and here she says, here, page, here's this page again. Here's your final exam, class. Good luck. Actually, you'll probably need super duper luck. What's all this stuff from chapter 100? And she's looking at all these problems. And by the way, this is what you guys get to look forward to in calculus. Well, not really, not that bad, but you know. Oh, people, I'm so sorry. I've handed out the wrong test. If you could just pass those back to me. Whew. Here's the exam you should have gotten. The other one was for the remedial class. Ah! And then she wakes up from her dream. The only thing worse than dreaming about math final is waking with the realization that you still have to take it. And then he's like, here, I polished your calculator. Here's my buddy Jason. He's so cool math guy. All right, moving on. Here is your extra credit. All you need to do is put your name on a piece of paper and tell me how many triangles you see. That's it. You give me the right number, you get tons of extra credit, just tons of it. But you got to get the right amount of triangles. So good luck, and give me that number and put your name on a piece of paper. All right, let's get to rotational symmetry. How many matches there are as you go once around is called the order. If you think of propeller blades like below, it makes it easier. Like this one goes around once, and it would be as it goes around one full rotation, it would land on this one once, and then it would be back to where it was. So it has an order of two, because it would two turns, as you go around once, it would land on each other twice. And this one would have three, and this one would have four, and this one would have eight, and so on with these pictures. But here's how you can really see it. So let's go to this website, and it really gives you a chance to see it. Okay, so this one right here says has an order of two. Watch this top little mark as it goes around halfway, and it was one, and then the other way was two. So as it went once around, it matched up on itself twice. As this one goes around once, it matches up on itself once, twice, three times. It matches up as it goes around. That's called an order of three. So you can have an order of as many times as it matches up on top of itself in one full rotation. All right, moving on. Is there rotational symmetry of order one? No. Not really. It's just if it goes around only once and matches up on itself, that's just, one time around. That's nothing. It's not really an order one. You don't have an order one. Here's some real world examples. A dartboard would have an order of 10. As you go around the dartboard, it would match up on top of itself 10 times, because this black one would go to here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The bronze star would have order of 5. 1, 2, 3, 4, 5. The carousel would have, oops, I lost count, too many. Yeah, it would be tons of them, probably 20 or 30 at least. Reflectional symmetry. We've already talked about reflections, so you already know that, but reflectional symmetry is when the reflection line is in the middle of the shape and one side lands or maps on top of the other side. That's called reflectional symmetry, not just a reflection. Here you can see the white line down the center is a line of symmetry called the mirror line, and one side matches up the other side. Same thing with the mountain on the lake. The line of symmetry runs left to right. It's not perfect symmetry because, the images change a little bit by the lake surface, but it's close. And again, you can pause the video if you need to catch up on those. Just moving on a little bit here. Here's the line of symmetry. Now you can see all of these examples down here show you reflection symmetry. They show you that a line can cut through a shape and one side would land on the other side. So it would cut through guitar and the sides would land on top of each other. Y equals x and y equals x would be lines that would do that, or y equals negative x. These are just shapes that, again, you draw a line through the center, you one on top of the other, and it would land on top. That's line of symmetry. There are 4 common directions, and they are named for the line they make in the standard XY graph. So y equals 0 is your x-axis, x equals 0 is your y-axis, y equals x, and y equals negative x. Those are the 4 common ones. I mean, you can pause it if you need to. And in shapes, there are shapes that have many lines of symmetry through them. Like an equilateral triangle, you'll see, has 3 lines of symmetry. You can cut right here, and the shape would fold on top of itself. You cut it through here, the shape would fold on top of itself. An isosceles is always going to have 2 lines of symmetry. This side would fold on top of this side. Scalene, no equal sides, no lines of symmetry. A square will always have 4 lines of symmetry, the 2 diagonals and then the horizontal and the vertical. Rectangle, only 2. The diagonals don't work in a rectangle because the sides aren't, all 4 sides aren't the same length. No lines of symmetry in an irregular quadrilateral. But a kite would have 1 line of symmetry there, exactly 1. And a rhombus where all 4 sides are equal, kind of like a square but not without the right angles, would have 2 lines of symmetry. You wouldn't have your horizontal and vertical in this one. So those are just shapes that have lines of symmetry where one side would fold on top of the other side. Regular polygons, regular means all the same size and all the same angle. Sides are equal, angles are equal. This one, equilateral triangle, we already saw before, 3 lines of symmetry. A square has, again, 4 lines of symmetry. A regular pentagon, 5 lines of symmetry, because you could go through each angle and it would be a line of symmetry. One would fold on top of the other. A hexagon would have 6 lines of symmetry. A regular hexagon were all the same sides. A regular heptagon, which is 7 sides that are the same, would have 7 lines of symmetry. Octagon would have 8, decagon would have 10, and so on as it keeps going. A circle would have infinite lines of symmetry. You could draw a line through the center point on any circle in any direction, and it would be a line of symmetry, as long as you go through the center point on the circle. So those are just polygons that have lines of symmetry in them, where you could draw a line in the shape and it would fold on top of each other. Lines of symmetry. All right, here's a couple of sample problems. Last 4 problems here. It says, which of the following transformations carries this regular polygon onto itself? Would a rotation of 40 degrees clockwise? It says 6 sides. So if you took 360 and divided it by 6 sides, it would equal 60 degrees. Okay, so what that means to us is that every 60-degree move, this side would then land on this side, and this side would then land on this side, and so on. So moving it 60 degrees would cause us to have this shape land on top of itself. That's what it means. So we're looking for a 60-degree rotation, which they don't have. But a reflection across L, if you folded the shape on line L, or if you flipped it over on line L, then they would land on top of each other. So this is the correct answer here. It would be a reflection on line L. These are not going to work. We need the 60-degree rotation here. Now this one has 5 sides. So if we took the whole all the way around once, 360 divided it by 5 sides, you would get 72 degrees. So 72 degree clockwise, counterclockwise, or clockwise, either way, and you're going to get it to work. So both of those work. So this one works, and this one works. Okay, so those would both make it land on top of itself. If you turned this 72 degrees one way or the other, this side would either land on this side, or this side would either land on this side. Now, are there any others? 30 degrees? No, that's not going to happen. It's just going to make it land up here somewhere. 90 degrees? No. Now, the order of this one actually has an order of 6. if you turn this around one rotation, it would land on itself 6 times because there's 6 sides. This one would have an order of 5. If you spun this shape, just spun it around, it would land on itself exactly 5 times. And I kind of want to show it to you. So I'm going to draw. I'm going to do that. Actually, I'm going to do this. Let's see if I can do this. I'm not promising anything. Just messed it up. Try again. Okay, so it's kind of off the cuff here. Something I didn't think about until just now. Okay, and let me make it clear again. Actually, let me just make it white. Let's grab it. Okay, so if I took this shape right here and I spun it, there's one order where it would land on top of itself. Or there's one. There's 2. There's 3. And I know my shape's a little off, but normally it would work. There's 3. There's 4. And then back to the beginning, you'd be back to 5. So its order is 5 because I could spin, and I went just once around because it started, all this stuff started on top. So I went one time around and it overlapped itself 5 times. That's called an order of 5. Last 2 here. Which of the following transformations carries this regular polygon onto itself? What a rotation of 30 degrees. Well, again, we have 6 sides. So if I take 360 again and divide it by 6 sides, I get 60 degrees. So 30 degrees won't do it. 30 degrees will be halfway to a spot where it would work. So that doesn't work. 72 doesn't work, but a reflection across L would work. If you folded this on top, it would land on right on top of it. If you flipped L around, this bottom part would be on top and this top part would be on the bottom. That is definitely the right answer there. A reflection across L. And a rotation of 60 also works. Any 60-degree rotation is going to make one side land on the other. And this one again will have an order of 6. Order of 6. One turn, and it'll land on itself 6 times. Now let's see. This one has 3 sides, so 360 divided by 3 sides equals 120 degrees. So if you turned it 120 degrees, this side would land on this side. And I see a 120 right there, so that would actually work. Now, are there any others that would work? 40 degrees? No. 45? No. 120 does work, and the other one doesn't. This has an order of 3. One time, you spin it around one time, and it would make it land on itself 3 times, so it has an order of 3. All right, so there is a little bit of rotational symmetry for you, and hopefully you got those, and I'll see you guys later.